Yes. Here we go.
So I'm on unmute now. Okay. Where's that coming from?
Hello, hello. I think we got it.
Okay. And everyone can see that? All right, we're good to go. Sorry about that, everybody. Everything is started. You're good to go. Okay. Just if there's questions, repeat. All right. Hello, my name is Jess Kaminsky. I am actually no longer a Brown student. I graduated last week with my master's in biostats. Today I'm going to talk to you about proportions and means in the context of statistical inference and estimation, and specifically estimation of confidence intervals. So we're going to go through some important definitions to sort of provide you with a foundation for things that are important for understanding the intuition behind confidence intervals. We're going to talk about what statistical inference is and specifically what estimation is, and then 1 and 2 sample confidence intervals for both means and proportions. So the first important thing that you need to understand is the law of large numbers. Simply, this just states that the more observations, the larger your sample is, the closer your estimates are going to be to the true parameter. So say you have a large population and you want to estimate what the true population mean is. If your population is, say, 1 million people and you just sample 1,000, that mean probably isn't going to be really close to the true mean. It might be if you're lucky, but it might be really far off from it. But if you have 1 million subjects and you have just under 1 million sampled, then you're going to be probably really close to the true mean. So I provided this graph to sort of illustrate this. You can ignore the math in here. But what this shows is this is a population of 10,000. And the true mean of whatever we're trying to estimate is 3.5. And we see that as our sample is really small, our estimate of the mean is really low and really high. It's very variable. Maybe we took 5 observations, a sample of 5, and we just got really unlucky and sampled the 5 smallest observations or the 5 largest. So we have a lot of variability in our estimate as the sample is small, but as our sample size increases and gets closer to the true population size, we're gonna converge to that true mean. The next thing that I want you to understand is the standard error. So in stats, we have a standard deviation, which is a measure of variability. Now, the standard error is the standard deviation or the measurement of variability of an estimate. So we take a sample from a population and we compute a sample mean. Now, the standard error is the variability in your estimate of that sample mean. So how right or wrong are you on average in that estimate? So the standard error and the standard deviation are different things. The standard error is the standard deviation of your sample mean, whereas the standard deviation is the standard deviation or the variability of your true mean. So the formula, how do you calculate the standard error? It is equal to that standard deviation divided by the square root of your sample size. Given this formula, we can see that as your sample increases, your standard error is going to decrease. This is the same finding from that law of large numbers. More sample, a larger sample size means a more accurate estimate and a smaller error in your estimate. So to further illustrate this one more time, this shows us, so the first plot on the top left, what we did here is we took samples of 5, so very small samples, and we did that 1,000 times. In each of those samples, we calculated a sample mean, and we've plotted those here. So we can say that the true sample mean is probably 5. That's where it's centered around, but we have a lot of variability. We're estimating outside of 5 and kind of far away from 5 fairly often. But as we increase our sample size, the center of our distribution is getting taller, and we're getting less variability and more precise estimates. Again, because our sample size is large, sample size is important. The last thing that is important for you to understand is the central limit theorem. So this says that the distribution of a sample mean of size n from a population where the true mean, we're going to call that mu. That's if we were able to sample everyone and take their mean, it would be mu. And standard deviation sigma, that sample mean has a distribution with mean mu. So the average is still the same. And the standard deviation is this sigma over root n, which is your standard error, a function of your sample size, right? So in all of these, our sample mean has a distribution where it looks like 5 is the mean, but the standard deviation is a function, or the standard error is a function of the sample size. As n increases, your amount of sampling variation decreases. And this applies to any distribution if your sample size is large. So regardless of your distribution, we're going to converge to normal as our sample increases. And so with this in mind, we can take our assumed normal distribution from a sample statistic, and we can convert it to a standard normal distribution. This is a normal distribution with mean 0 and standard deviation 1. You standardize it by taking, sorry. You're going to take your estimate here, which is x bar. You subtract the mean and the standard error. This is just the formula for standardizing something. What this is going to do is it's going to cause your test statistic to be normal, mean 0, standard deviation 1. This might be a little bit confusing, and you might be unsure why I'm showing you this. I hope in a few more slides it will make sense. This is really important for us to make inferences about and create confidence intervals. Okay, so I told you at the beginning that I'm going to talk to you today about estimation, but where does estimation fall? Gabby talked to you last couple weeks ago about hypothesis testing. How are all of these things related? So you have statistical methods, and here we're talking about statistical inference. It comes in 2 different types, hypothesis testing and estimation. So as I said, Gabby talked to you about hypothesis testing, and today I'm going to talk to you about estimation. The thing with this is we can draw the same conclusions about our data using these 2 techniques, but with estimation, you might be able to get a little bit more information. So statistical inference in general, we're dealing with inference from a sample to a population. We want to be able to make inferences about the whole entire population just by taking a small sample from that population. And we hope that the sample that we take is going to be truly representative of the population. And we can use estimation and confidence intervals to reflect the uncertainty in our estimates. So this is what it might look like. You have your target population and you draw a small sample. I think it makes sense that you could sample many times and you could get completely independent samples, groups that aren't overlapping. Maybe you could take another sample and this time it's these 3 individuals plus one other one. So we want to understand, if we take another sample of the same size, how similar would their estimate be to this one? How different might it be? How can we measure the variability in the estimates if we took more or less samples? And then finally, how can we provide that interval estimate, which is our confidence interval? So I've been using the word sample and true means a little bit. The characteristics of the population, if you were able to find the true mean, standard deviation, or proportion of something in the entire population, if you were able to sample everyone, you call those the parameters. The estimate of the parameters that you calculate from your sample are called statistics, and those are your sample mean, your sample variance, and your sample proportion, which are being used to, again, estimate and make inferences from a smaller sample about a larger population. And our goal is to find the statistics that provide estimates of parameters that are accurate on average and precise to our true population parameters. So in real life, we don't know the underlying distribution. We don't know what the whole population looks like. We only know what the data in front of us looks like. And this comes from that single sample that we take. Based on our knowledge and distribution of the sample, we tend to assume a distribution. Hopefully it's normal, but there are some other distributions that we might assume as well, and I'll go over later why you might assume one or the other. Then, based on the data and our assumed underlying distribution, we try to make a guess about what the true parameter values are. So we're guessing the unknown value. I think the main thing that I want to point out here is this is how we write the sample statistics. We write X bar for the sample mean, and then we write that mu for the true mean. S squared for the sample variance, and then sigma squared for the true variance. P hat for the sample proportion, and then P or pi for the true population proportion. So I've indicated that there's two sorts of estimation. There's point estimation and there's interval estimation. So point estimation is just getting one single value. You take a sample, you calculate their mean on something, you have a point estimate. Maybe it's close to the true mean, maybe it's not. Interval estimation, we're gonna find a way to provide a range of values that reflects our uncertainty around our estimate. So point estimate is a single value based on observations from one single sample that we take. The problem with this is that we're unable to determine the accuracy of our estimation. Like I said before, we might have gotten really unlucky and got the 5 lowest observations, and it's going to really look like our mean is much lower than it is. Or same if we got the 5 highest observations. Or we got lucky and we got the 5 middle, and just in this one sample, we really estimated the true mean. So as an example, this looks like we take a random sample of boys aged 13 to 19 to obtain a point estimate of the mean weight among teenage boys. We obtain a point estimate of the mean weight to be 135 pounds. If you're just doing point estimate, that's it and you're done. But again, you aren't really able to draw conclusions about the uncertainty or how accurate this is in relation to the true estimate. Interval estimation, this is what a confidence interval is. It's a range of values based on, again, observations from just one single sample. And the reason I say one single sample is because we can do this repeatedly. And then we can also make statistical inferences about the repeated sampling. It provides intuition about the accuracy in the estimation of your true parameter. And an interval is provided in terms of probability. So if you had done your work, taken your samples, in the end, you would be able to say something like, we are 95% confident that the true mean of teenage boys lies between 120 and 150 pounds. I'll talk a little bit later about exactly what that 95% confident means, but I just wanted to show this as a starting example. And then also that 95% can change. We decide what that number is. So for the purposes of this talk, we're going to talk about mu for the mean, which is for quantitative, continuous type data, and P for proportion, percentage, fraction, or rate for qualitative data. For mean, we might be looking at average life expectancy. And for proportion, we might be looking at the proportion of women in some population who experience miscarriage. And so anytime we're doing a data analysis, the first thing we're going to do is define our target parameter. A lot of times, statisticians also look at variance. So all of the same things that we're going to do today, you can apply to variance as well. So why confidence intervals? Why not just a hypothesis test? Why not just a point estimate? So you want to estimate a population parameter. As an example, your population parameter is a single fish in a river. And you want to capture that fish, just like you want to capture the target. When you use just a point estimate, every time you sample is like you're spearfishing. Maybe hypothetically say you're going to catch a fish every time, but you don't know if you're catching the right fish every time. And you also don't know if the right fish was right next to you. You don't know if it was miles down the river. Whereas with a confidence interval, you're casting a wide net, and every time you cast it, you have many more fish inside, and the chances that you've captured it are much higher. So now sort of starting to think more with math, what does a confidence interval look like? I think maybe I could have reversed these two. So I'll start with this line. You have an estimate, and you add and subtract some margin of error to get an interval that surrounds the estimate that you've created. What does this margin of error contain? It contains a critical value. For now, we're just going to understand that as a number that you can look up in a table. And then your standard deviation times your standard deviation of your estimate. So if we're interested in the sample mean, the confidence interval for a sample mean might look like the sample mean, both plus and minus, some number you look up in a table, critical value, which is related to the distribution that you assume, times the estimated standard error. Standard error, because as I showed you all the way in the beginning, that is the standard deviation of a point estimate. It captures the variability. Under the central limit theorem, we can assume the sample mean is approximately normally distributed for large samples. There are a lot of different rules for what is large. Even when I was creating these, I found many different rules. But the one that I'm going to stick with here is 30. Your sample size 30 is considered approximately large. Now, our formula for our confidence interval looks like this. This is no different than the confidence interval I just showed you on the slide before. I just added in the symbols. So X bar is your sample mean, plus and minus. Z, because we're assuming that standard normal distribution. This is information about the test statistic that I will show you. And then times sigma over root n, which is our standard error of our estimate. Okay. Before we get into that more, what exactly is a confidence interval doing? What is a 95% confidence? This image is meant to depict a standard normal distribution, so a normal distribution with mean 0 and standard deviation 1. So an important thing to know is a standard normal has, as I said, mean 0, but it's also symmetric about 0. Now, in a 95% confidence interval, we want to capture the bounds on either side that capture 95% of our data. So here, for the standard normal, it happens to be plus and minus 1.96. So what this means is in between these two bounds lies 95% of our data or observations. And then conversely, we have 5% of our data outside of the tails, 2.5% here and 2.5% here. So what we're doing when we calculate a confidence interval is we're using this idea, but we're applying the sample mean that we calculated and the sample variability, so the standard error, to this idea and to this distribution to get the bounds from that data that do capture this 95%. And then when we do that, with 95% confidence, 95% of all generated confidence intervals will contain the true population parameter. So what does that mean? So like I said, we can do this many times, and then you can end up doing statistics on this repeated sampling. But what this looks like is if this is your whole true population, one time we're gonna sample, it's a sample of size n. We're going to calculate the sample mean for that. We're gonna add and subtract the bounds. 1.96 is just that number from the table. And this is our standard error. And then in this case, it gave us a confidence interval of 15 to 28. So from the information in this sample and the information about this population, we determined that, or we hypothesized that between the bounds of 15 and 28 lie 95% of our data. We can do this as many times as we want and end up with as many confidence intervals as we want. So what 95% confidence means is that if we were to do this 100 times, 95 of these intervals we expect 95 of these intervals to capture the true mean. It's not that there's a 95% chance that your mean is within that interval. It's that if you do this over and over again, we expect a 95% hit rate, or 95% of our intervals are going to capture what we're looking for. And then this just shows that same idea, just depicted differently. If this vertical bar is your true mean, and the horizontal dashes are different confidence intervals you calculate, we see many of them capture it, but some of them might miss sometimes. Does anyone have any questions so far? Okay. Okay. So constructing a two-sided confidence interval. Again, this is the formula that I've been showing you. I think the thing that I want to go over with this is sort of this Z notation. So we have Z 1 minus alpha over 2, and then that becomes Z some number, which then that's easy to look up in a table. Once you have Z and that number, you just look it up in a Z table or a T table if you're doing a T distribution. But how do we get there? So alpha is based on your confidence level. So if you want 95% confidence, alpha is going to be 5%. It's what's ever left over. If you want a 99% confidence interval, alpha is going to be 1% or 0.01. And so when we're trying to figure out this little number here, we're doing 1 minus alpha, so we'll call it 5% for now, 0.05. And the reason that we're dividing that by 2 is because we're splitting it into the two tails. So this Z 0.975, what that's really showing us, let me go back here so I can show you, is that at this line 1.96 and everything to the left, that's 97.5% of our data. And then we can just use the plus and minus of that because we know that this distribution is symmetrical. And then once you have that, you can look it up, but 1.96. And then that is going to be your critical value, your Z-score for your test statistic. So we can calculate any size confidence interval that we want. I just listed these here as some common ones, 90, 95, 99%. And then in a few slides, we'll talk about the implications of raising and lowering those levels. Okay, so say you set out to calculate a two-sided confidence interval for the mean. You might want to begin by asking yourself these questions. Do you know the population standard deviation? So this means, do you know what the variability level is in the true full population or not? If you don't, you're going to use a t-score instead of a z-score. If you do, and your sample size is above 30 or reasonably large, you're going to use a z-score. If it's not, if it's too small, you're again going to use a t-score. What is a t-score? So a student's t-statistic, or the t-distribution, is similar to a normal distribution, which is why we use it here. As your sample size increases, it's going to converge to a normal distribution as well. The difference is this has more variability. You see those tails are stretched out farther, so you have a wider distribution. One feature of the t-distribution is that there's something called degrees of freedom, which is based on the sample size. So your degrees of freedom is just going to be n-1. And you use that to figure out which curve you're looking at. This is the wrong picture, sorry. This is supposed to be, what this is meant to show you is you have this blue line for the t-distribution, and then there's going to be many more lines in between. And this is for, I don't know, say degrees of freedom 3. But then the next one is going to be degrees of freedom 4. And the more degrees of freedom you have, the closer you are going to be to normal, which sort of justifies our use of it in generating confidence intervals when we don't know the true standard deviation and when our sample is too small. Okay, so we're going to go through an example of constructing a confidence interval for the mean. So we know, say, that white blood cell count follows a normal distribution with an unknown mean and a known standard deviation of 1200. So we know, through some way, we know that the truth in the population is 1200. Then we randomly select 12 people and count their white blood cells, and we get these 12 observations. The first thing we do is just calculate the sample mean, 7877.25. That's our point estimate, right? And we could stop there, but we want to keep going and create a confidence interval. Again, our sample size is 12, and our standard deviation is 1200. So we can just plug in those numbers to the formula for the confidence interval, and we get this as a confidence interval. Now, what does this mean? So we have 95% confidence because we used that critical value that's associated with 95% under the curve. But as I said before, this does not imply that our true value lies within the interval with a 95% probability. It means if we did this same calculation from samples 100 times, we hope 95 of them will capture the true value. But you can't make explicit statements about any single interval and whether or not it will capture the true parameter that you're searching for. So again, this doesn't tell us that the probability that mu is between those limits with 95%. It's important to remember that mu is constant. It's not something that's changing. It's just something that we don't know. And then again, if we took many samples, we hope 95 of them would come close to actually capturing the true. So that example continued with the white blood cell count. Say that the true mean number of white blood cells is actually 7,840. The confidence interval we constructed does actually contain that value, but it's important to know that we could have sampled a different set of 12 men, and the means could have been different. The data is random, which means the sample mean is random as well. So this shows us performing that sampling and calculation of the point and interval estimate 100 times. and plotting the range of the interval, where the true mean of, I think it was 7840, in the middle, and these red ones don't capture the true mean. So in this example, we constructed a 95% confidence interval. But this 95% is somewhat arbitrary. You can have, again, 99% confidence or 90% confidence. Does anyone notice, how do these intervals change? Even if you don't remember the 95%, if you compare the 99% to the 90% confidence interval, what's the difference? Yeah, it's bigger. So in general, right here, as we increase our confidence, we have a wider confidence interval, which I think is kind of intuitive. If you want to be more confident that your interval is going to capture the true value, you're going to widen up that confidence interval and give yourself some more space to actually capture it. But what are the pros and cons of having a wide versus narrow confidence interval? A narrow interval, there's less uncertainty, but with the wide interval, you have more coverage to capture possible deviations from what you expect. So again, as your confidence level increases, so does the width of your confidence interval. As your sample size increases, your confidence interval will get narrower because you're more confident. As your standard deviation gets smaller, also so does your confidence interval. And this comes really from this formula, right? As these things are, well, as the sample size gets bigger and the standard deviation gets smaller, that's going to cause whatever we're adding and subtracting to be a smaller value. And keep that interval more narrow. Okay. So let's say you read an article and it says, we polled the electorate and found that 45% of voters plan to vote for Hillary Clinton. The margin of error for this poll is plus or minus 3.4 percentage points, 19 times out of 10. So we can actually sort of disentangle this and get most of our elements of a confidence interval from this statement. So 19 times out of 10, that's 95%. So that's our level of confidence at the rate at which this is happening. The margin of error, plus or minus 3.5%, indicates that the 95% confidence interval is this. So 45% of voters on average, with some margin of error that's plus and minus 3.5%, gives us this confidence interval. So how do we interpret this statement? If we were to take 20 such polls, 19 of them would capture the true percentage of people who are going to vote for Hillary Clinton, but not that there's a 95% chance that this confidence interval captures the true percentage of people who are going to vote for her. This example, I also wanted to show that this can give you an idea of the precision of your point estimate. So the difference between the upper and lower bounds, which is 6.8 or double your margin of error, is going to basically tells you that we're off by 6.8%. Is that a lot? I'm not really sure. It might depend on the unit of what you're measuring. So if a 1 unit increase means a lot for your data, then it might be important. But if a 1 unit increase is really negligible, then a margin of error of 6.8 is probably not a lot at all. So we've been talking about two-sided confidence intervals, which is capturing those bounds in the center of the data and leaving a symmetrical amount out on each side. But what about one-sided confidence intervals? So in some situations, we might be concerned with just an upper or just a lower limit. So for example, the distribution of serum cholesterol for all 20 to 74-year-old males in the US, the population mean is unknown. The standard deviation is 40 milligrams per 100 milliliters. We draw a sample of 12 and obtain a mean of 217 per 100. What value can we be 95% confident that the population mean is no bigger than? So in other words, what value can we fill in here where the probability that the mean is less than this is 95%? So that looks like this. Instead of splitting up our 5%, we're leaving it all on the end because for some reason in this data set, we're more concerned about the upper bound, and that's all that we care about. In this situation, the only thing that's different is you're now going to find the z-score or the other test statistic that's associated with 5% to the right and 95% to the left. And then you're only going to add. Instead of doing the confidence interval where you plus and minus, you're just going to add and get that upper bound. Okay. So that is confidence intervals for means with just one sample. Now we're going to talk about confidence intervals for proportions with just one sample, which is really quite similar. The only thing that changes is the formula, but the intuition and generally what you're doing is the same. So we want to estimate the prevalence or the proportion of women in the population with malignant melanoma in 45 to 54-year-old US women. We select a random sample of 5,000 and 28 are found to have malignant melanoma. So if X is our disease status, 1 means they have the disease, 0 means they do not. We're going to call P the prevalence or the proportion that we're interested in. How do we estimate this? Well, we have a sample of 5,000 and we found that 28 of them have it. So the sum of our X's is 28 because it's 1 if they have it and 0 if they don't. Now, if we average the X's, which is just the sum of the X's divided by the number of them, we get 0.0056. So this is the proportion of the women in the population who have the disease, but it's also just an average. So X bar does estimate here the proportion of women who have malignant melanoma, but it's also a proportion. Okay. So the expectation, notation is for the mean. So the mean of P, the proportion of women with melanoma. The variance and then the standard error. So again, the standard error of a proportion is going to look like this, which is going to be, again, important for that confidence interval formula. So what does this look like? We calculated P hat, our sample proportion for the sample that we took. We can calculate the standard error by just plugging in P, again, to this formula. And this is our standard error. And now we basically have everything that we need for calculating the confidence interval. So since we established that P hat is a sample mean, we can use, again, the findings of the central limit theorem to see if the assumptions hold. Yeah. Oh, yeah, sure. Yes, the bottom one is the estimate. So we established that P hat we can also consider to be just a mean. So we can use the findings of the central limit theorem if the assumptions hold to generate a confidence interval. We need to have a large sample size. Now, when we were working with means, the other thing we needed was, well, approximately normal and a large sample size. Here, the other thing that we need is sort of this general rule. And again, this rule changes just like 30 as an appropriate sample size. This, I've seen different values for this, but this is the one that I'm going to stick with here. So you want your sample size times p hat times the inverse of p hat, 1 minus p hat, to be greater than or equal to 5 in order to be comfortable with your findings and say that you have valid assumptions. So the confidence interval for a proportion, the formula is here. So the only difference is we're putting in p hat for the parameter and then the standard error of p hat instead of the standard error of the mean. Okay, so if we want to construct a confidence interval for the proportion, we have a weight loss program for 40 participants, and a participant is considered successful after losing 5 or more pounds after 3 months. And 10 of our participants are successful. So our success rate, or our proportion here, is 25%. It's our sample. And then we can just use those numbers to plug right into our formula for our confidence interval, and we get this as our confidence interval. And then we want to check, is our approximation valid based on this rule, which n times p times 1 minus p should be greater than or equal to 5. When we plug those in, we get 7.5 for that value. So yes, we can be comfortable and confident in our approximation. Does anyone have any questions so far? This right here. So this is just the rule. It's a rule that you can find. And sometimes this varies. I've seen this number be 15. I've seen this just be n times p instead of n times p times 1 minus p. So this is something that there's disagreement about. But for here, this is just the rule that I chose to work with.
Is that rule ever named?
Not that I know of. Throughout here, that might just be being a little messy and not paying attention to it. It just should be big C. Yeah. So everything we've done here is one sample inference, which just means that we've taken one sample from one population, and we've done some math and inferring with it. But what if we're interested in comparing two different populations? Two populations that are independent, two populations that are dependent. So we can do two sample inference. We want to compare some unknown target parameter between two populations. So our question might be, do males or females perform better at some given task? Does an individual feel better before or after taking some drug? So the first question, males or females, that would be an independent population. It's two separate groups of people, and we're just comparing them. The second question, does an individual feel better before or after? Because there's some inherent dependencies on the fact that it's the same person and that we're comparing before and after, that would be considered a dependent population. But in both scenarios, we want to estimate the difference between some parameter and get a point estimate, and then build a confidence interval to draw conclusions about the differences among those samples. So here, our potential target parameters change. Instead of just being mu or p, it's going to be mu1 minus mu2. So the mean in population 1 minus the mean in population 2, or the same with proportions. So the mean difference, or the difference between proportions. So I'll start with the means. We're interested in the difference of population means between two different samples, and we want to estimate the mean difference. We're going to call mean 1 the mean BMI among non-diabetic women, and mean 2 the mean BMI among diabetic women. We want to compare them and see if they're different. So we have this data, and we're lucky enough to know the true population standard deviation. These are our sample, there should be a bar here, our sample means and the sample sizes from those two populations. Again, we can first just generate a point estimate very easily by subtracting those two, and that difference is negative 3.64. And then we want to generate a confidence interval. So everything's the same. Sorry, this got cut off. We put our point estimate first, and we add and subtract some critical value, and then the standard error, this is the formula for the standard error of this mean difference. So a lot of this is understanding this, I think, is just understanding the intuition first, and then knowing what to ask yourself and look for when you're calculating these things, and then looking up the specific formulas for that. So if you plug in, you're going to get this value, the end interval here, -5.2 to -2.06. So what does this mean? We are 95% confident that the true mean difference lies in this interval. Now, if you were to do a hypothesis test with this same data, comparing mean 1 versus mean 2, you would get a significant result. And the reason that we know that is because this confidence interval doesn't contain 0. So the fact that this confidence interval doesn't have 0 in it means that we're saying we don't think that there's a significant probability of the difference between these two things equaling 0. Therefore, we think there's a significant difference between them. The mean BMIs of diabetic and non-diabetic women are significantly different in this study. So again, I said some of this is just knowing what to ask and which formulas to look up once you understand the intuition behind it. So in this example, we knew the true population variances. We didn't make any assumptions about whether or not the population variances in the samples were equal. We assumed that the mean difference was approximately normally distributed because we used that z-score. And then we know that the samples were collected from 2 independent populations. So for example, the variance, I mentioned that we didn't make assumptions about whether or not the variances are equal. But you can assume that the variances are equal or that they're unequal. And the main thing that this is going to do is going to change your standard error formula. And it can get quite complicated if you decide to, so pooling the variance means that you're assuming that they're equal, just combining them. Unpooled is assuming that they're unequal and separating them, but you have to account for that so the formulas can get kind of messy. Some recommend conducting a hypothesis test or an F-test to determine statistically whether or not there's a significant difference in the variances before then continuing out these formulas. But some don't necessarily agree with that because the test can be unreliable. Sometimes others just recommend always assuming they're unequal because this is a more conservative test and you could trust the results more even if your variances are actually equal. So that's one consideration. Another, as I said, was the independent or dependent populations. So two-sample inference for dependent means. These are paired measures. So some examples of these are pre- and post-test measurements on the same subject. Ocular measurements on right and left eye in the same subject. IQ scores in twins or husband-wife pairs. Measurements from 2 methods of conducting an assay on a patient sample. So these are all things that are inherently dependent, and so we need to treat them differently than we would to independent samples. So I'm not going to go too much into the math of this, but the general process is you'll have 2 measurements for every subject, and you're interested in the difference between them. So the first thing you're going to do is just create yourself a new variable that is the difference between each measurement on each subject. Once you do that, this now actually simplifies to just a 1-sample test on that new variable that you've created. So this is a formula for the confidence interval for these paired mean difference. So the mean difference, the lower bound, is going to be that difference that you calculate. Here, instead of z, I put in t, but again, right, depending on our situation, we'll be using t or z, and then the standard error of our difference. That's all I'm going to say about paired samples, because, as I said, once you get to here, it really becomes just a one sample confidence interval for the mean. Okay, two sample inference for proportions. So we're going to assume normality via the central limit theorem as long as our sample size is large enough. And then I showed you this general rule for proportions with one sample. Now we just need to make sure this rule is satisfied for both sets of our populations. We still need to be careful using appropriate methods and approximating, just as we do with the one sample methods. But again, just like every other one, the confidence interval has the same general form. And for this one, it might look like this. Your difference in sampled proportions plus or minus your test statistic. This one is the Z of 95%. And then the standard error of the proportion, the difference in proportions. Okay. So let's go through an example of this. So this is our data, and we're looking at some drug for intervening with some sort of fatal outcome. So we're looking at how many survived and how many did not survive based on taking drug A or drug B. We're going to call, based on this sample that we have, the probability of being alive after taking drug A. Sample probability, P2 hat, is 16%. P1 hat is 34%. So the point estimate for our difference is 18%. So interpretation of just that point estimate is, in this study, there were 18 excess subjects alive per 100 for those treated with drug B, as opposed to those treated with drug A. What is the estimated difference in mortality, and is this difference statistically significant? We can use the confidence interval to determine that. So this is the formula, and then this is just plugging it in. We end up with this 0.04 to 0.32 as our estimate. Now, how do we interpret that? So the first thing, the confidence does not contain 0, indicating a significant result. We don't have much confidence that the true difference is 0, which would indicate that they're the same. There is a statistically significant difference between the two proportions. We can also say we're 95% confident the true difference lies between 4 and 32%. Now, this confidence interval includes all positive numbers. And we subtracted P1 from P2. So that gives us some indication. We can infer that in general, P1 is greater than P2. The probability of being alive after being treated by drug B is greater than for drug A. Okay. Now, lastly, I hope these sort of diagrams can help bring this all together a little bit. If you want to do a one sample confidence interval for the mean, you know your target parameter is mu. You want to capture that somehow. The first thing you need to figure out is, do you know the true population variance or not? If you do, and you have a large enough sample size, again, by some rule 30, some other rules say it's more or less. You can assume a normal distribution with a large enough sample and use Z. But say you don't know the variance. First, you need to figure out, should I assume these variances are equal or unequal? Do I want to do something to test whether or not they are equal or unequal, or do I just want to make an assumption? Based on that, you can fall into one of these for equal or unequal variances. You're going to use T to approximate Z because you don't know the true variance. If you assume that there's equal variances, you're going to use the pooled estimate of the standard deviation. If you assume unequal variances, you're going to use T and the unpooled estimate of standard deviation. I didn't show you these. The pooled one isn't so bad, but the unpooled estimate, it's like a very, very long kind of crazy formula. But if you're using some sort of software, I assume that this is just an option that you would plug in. And then you sort of have the same intuition with the proportion. And then if we're looking at two sample confidence intervals for the mean difference, first you ask yourself, am I looking at independent or dependent samples? If you're looking at dependent samples, it's not so bad. You compute the difference and then you treat it as a one sample confidence interval for the mean. For independent samples, again, we can look at variance known, variance unknown, variance equal, or variance is unequal. So I hope that helped provide at least some sort of intuition of how to calculate these things and the questions that you might want to ask when you're doing this. And so lastly, just sort of what I think is a comprehensive list of the things that you want to consider when you're doing this sort of inference and estimation. What's your parameter of interest? Is it the mean or is it the proportion? Or maybe it's the variance? Do you have one or two samples that you're comparing? What's your sampling procedure like? Are you ensuring that you have a random sample that is hopefully representative of your true population? And how can you do things to avoid bias? Is your sample size large enough to make the assumptions that you want to make and for them to be considered valid? Are your samples independent or dependent? Is your variance known or unknown? If your variance is unknown, do you want to assume that they're equal or unequal? Do you want to test for whether or not they're equal or unequal? And that is all I have. Does anyone have any questions?
Variance known and unknown, that's population variance.
Yes.
And can you think of an example when you would know that? In like a study or something?
When you would know that?
Yeah, like just an example you worked on where you knew the population variance.
I can't think of, it's something that we use for just presentation to describe, but I can't think of a time where I've legitimately known the population variance. And so typically in practice when you're doing this, my first step is to go to an F test for equality of variances and do that, and then use that to carry on my analysis. Yeah. So since the T is given sigma, we will still use populations, but if you don't know sigma, you would still use Z if your population is large enough? Yes. Yeah. Any questions on Zoom? All right, thank you. I think, do they have the surveys? Okay. Thank you. Stop share. Yes. And anything.